So are we in agreement that this is where we stopped so that I can continue, students? Please confirm.
Yeah. I remember something like dipole moment.
Yes, actually, this was my last explanation as to why ionic compounds are soluble in water. And we say that water is a polar solvent, and I explained why water is a polar solvent. We will be actually discussing the polarity of the bond much later. But what I simply said is that when you have water formed, water is formed, let me pick, when we talk about water, water is like this. There is hydrogen here, and there is another hydrogen here. Now, the sharing of the bond is such that, let me admit students. Let me see. Students have to be admitted. Correct. So we say that these two elements have different electronegativities, and therefore you would expect the electrons to be closer to oxygen than they are closer to hydrogen. So you will have the shared electrons closer here. I want to see whether I have admitted. I'm still admitting students, so bear with me. Good. So you would expect something like this. Now, what does it therefore mean? These electrons here are closer to oxygen than they are closer to hydrogen, and that means that this hydrogen is almost losing electron. This hydrogen is almost losing an electron. And what happens when an element loses an electron? When an element loses an electron, it becomes positively charged. So this hydrogen here is almost becoming positively charged in the sense that it is almost losing an electron, but it has not completely lost. And that is why we give it a partially positive charge. This is also partially positive. Now, this hydrogen, this oxygen here is almost acquiring 2 electrons, but it has not fully acquired. Therefore, we give it a partially negative charge. Now, because of this, you find that water is polar. The polarity is as a result of these charges. That results because of what I have already shown. Now, this being the case, then if you bring a ionic compound is in the form of M plus and the A minus, whereby the A minus, this one is the anion, while this one is the cation. Now, when you bring this one to interact with water molecule, there is going to be interaction of the ionic charges so that the partially positive hydrogen terminals are going to attract the anions, while the partially negative oxygen atoms are going to attract the cations. And in that process, some interaction will occur, and the interaction will cause the breakdown of the lattice. And when that happens, then we have formation of an aqueous solution. So that's why we say that the lattice breaks up and the ions mix up in water, therefore dissolving. This is when we have the formation of an aqueous solution. Now, the other property that we can look at is the electroconductivity of these ionic compounds. And we are saying that ionic compounds are going to conduct electricity either in molten states or in aqueous state. That is how they conduct electricity. Why does this happen? Now, this happens because for an electric current to be transported or for an electric current to be conducted, one, there has to be charged particles. And number two, these charged particles must be mobile. That's why we are saying that in order for a substance to conduct electricity, it must possess charged particles that can move. It must have some mobile charged particles, and these charged particles could be either positive or negative. Now, what happens in solid? What happens in solid is this: that although they have, I'm trying to pick something here so that I can highlight. So when we talk about solid ionic compounds, these compounds, although they have positive and negative charges, now in the solid state, these particles are held together by very strong electrostatic forces, and therefore the negatives and the positive charges cannot move. They are not mobile, or they are immobile. But now when we melt them, when they are either molten or dissolved in water, the charged particles now become mobile in the sense that they can move from one place to another, and in the process, they can conduct an electric current. So they can conduct electricity in the solution. So an aqueous solution or a molten solution of an aqueous substance is what we call an electrolyte. Actually, the basic definition of an electrolyte is a substance which is capable of conducting an electric current in either molten state or aqueous state. So a good examples of electrolytes are actually ionic compounds, because when they are molten or when they are dissolved, they can conduct electricity. There's a student who has left. Okay. So we continue. The other property is that these ionic compounds or the crystals can break up easily, or they can shatter easily. And why does this happen? When force is applied to the crystal, then that particular crystal will be forced to have the like charges coming together. So when force is applied to the crystal, the layers of the ions in the crystal structure can slip so that the similarly charged ions are next to one another. So when you apply some force on a crystal, then it's like you are forcing the positively charged particles to be close to each other and the negatively charged particles to be close to each other. And when that happens, then there occurs what we call electrostatic forces of repulsion. So that now when that repulsion takes place, like you can see, there's a hammer here, and that hammer is applying pressure. This star here is a pressure which is being applied on a crystal lattice. So what happens then, you'll realize that it's like we are trying to twist the structure so that these two are positively charged particles, they are together. These two are negatively charged particles, they are together. So a number of them are going to be aligned that way. And when this kind of alignment happens, then there is going to occur what we call electrostatic forces of repulsion. And when electrostatic forces of repulsion occur, you can see there is a repulsion between these two particles. There is also repulsion between these two particles. There is repulsion between those two particles. Now, that repulsion actually causes that particular solid to shatter. So that is why the shattering happens. So we move on, students. Then we look at what we call the electronic configurations of ions. When you talk about electronic configuration of ions, we may look at the electronic configuration of cations and the electronic configuration of anions. So when we look at the main group elements, and we talk about the main group elements, here we are talking about the S and the P block elements. Now, those elements may actually form ions by either losing electrons or gaining electrons. And when this happens, they actually do so to attain an noble gas configuration. And here we are simply looking at group 1 and group 2 elements. Now, when you look at group 1, they only lose 1 electron. Group 2 are going to lose 2 electrons, and they form cations. Now, those groups actually are predominantly going to form ionic compounds. And these are the ones that are found at the leftmost of the periodic table. So what I am going to show next is what happens in the ionization energies of these particular elements, the first ionization energy, the second ionization energy. And this is what I am showing here. And I'll spend some time explaining this slide. Now, ionization energy has been discussed before. So here we have a table of ionization energies, and of interest is the trend of the ionization energies as you move. Now, this one, when you see this blue partition here is showing this side and this side. Now, the side that you are seeing here, the side that you can see here is the side that shows the trend in the electronegativity, in the ionization energy of these atoms before a noble gas configuration is attained. Now, what you see above the yellow, what color is this? What color is this?
Blue.
Blue, okay. Let me confirm from you. So what you see above the blue color here is the trend in the ionization energy of the same elements after a noble gas configuration has been attained. And now I want us to look at what happens here in sodium. Sodium is a 3s1. Because if I was to write the electronic configuration of sodium, we have 1s2, we have 2s2, we have 2p6, and a 3s1. So this first ionization energy is the energy required for the loss of this electron. And what happens after the first ionization energy, you get this kind of a configuration. You get a noble gas configuration. And that is why for you to remove another electron, that electron is supposed to be removed from a 2p6 configuration. You realize that the second ionization energy is significantly higher than the first ionization energy. Because in the second ionization energy, you are actually attempting to remove an electron from a noble gas configuration. And this continues as you move. The other thing is, the moment you remove an electron, then you have increase in the effective nuclear charge, and that also increases the energy required for an electron to be removed. Now, again, you can see that we have magnesium. Magnesium is going to lose the first electron, and it is going to lose the second electron. Now, when those electrons are lost, then you are left with a noble gas configuration. Why? Magnesium is 1s2, 2s2, 2p6, and 3s2. So the first ionization energy will be involved in the removal of one electron here. Then a second ionization energy will be required to move the second electron. But now you can see that the first ionization energy and the second ionization energy are different in the sense that the second ionization energy is higher than the first ionization energy. One, because the moment you remove one electron here, then the effective nuclear charge increases and the remaining electron is held by stronger forces, than the other electron, and therefore you can see the energy required to remove the second electron is higher. Now, the moment you remove the first and the second electrons, then you are left with this kind of configuration, and this configuration is a noble gas configuration. A noble gas configuration, you know that it will require a lot more energy, that is the third ionization energy, a lot more energy for already a noble gas configuration to be broken down. And that is why you can see from 1,451 all the way to the 7,733, the energy difference here is a lot, because already here you are trying to remove an electron from an already established noble gas configuration. Then when you look at aluminium here, aluminium is 1s2, 2s2, 2p6, 3s2, 3p1. Now, the first ionization energy is the energy required to remove this first electron here. This electron here, that is the first ionization energy. Now, look at what happens in the second ionization energy. Now, the second ionization energy is the energy required to remove an electron here, while the third ionization energy will be required to remove the second electron. So by the time we are getting to the third ionization energy, then we have already removed those electrons. So that the fourth ionization energy now is the energy required to remove an electron from a P6. And that energy will be very, very high, because we are trying again to remove an electron from a noble gas configuration. Now, important here to consider is, can you look at the trend in the first ionization energies of this? Remember, we generally say that the first ionization energy has a trend as you go down a group. Now, look at what happens here. Now, this is 496 for sodium. This is 738 for magnesium, and then it lowers again for aluminium. Why? Let us just compare magnesium and aluminium and ask ourselves how much energy will be required to remove the first electron. So let me again draw the electronic configurations of this. So magnesium is 1s2, 2s2, 2p6, and 3s2. While for aluminium, we have 1s2, 2s2, 2p6, 3s2, and 3p1. It should be 3p1. Now, when we are looking at the first ionization energy of these two,
Excuse me, sir.
Is there a student who has a question?
The configuration is still very wrong for aluminium.
1s2, 2s2, 2p6, 3s2, and 3p1.
You've written 3 as 3, then
No, it should not be like that. It is 3s2. 1s2, 2s2, 2p6, 3s2, 3p1. That should be the correct one, isn't it?
yeah.
Now, what I want to explain here is this. If you look at the first ionization energy, we are just comparing the first ionization energy in magnesium and in aluminium. You realize that the first ionization energy in magnesium is higher than the first ionization energy in aluminium. Why? In magnesium, you are trying to remove an
This
electron.
angle. Let's complete the lesson.
Uh,
I have in but
somebody has not muted.
Okay.
A student is speaking in the background. So in magnesium, you are trying to remove an electron from a fully filled s orbital. And for you to remove an electron from a fully filled orbital, remember this is a stable configuration. And therefore, for you to remove one electron from here, you can see that a lot of energy is going to be required. For aluminium, you are actually removing a p1 electron. A p1 electron is loosely held and completely shielded by the inner orbitals. And that is why it is easier to remove a p1 orbital in aluminium than it is to remove an s orbital in magnesium. So that brings about the difference in the ionization energies that you can see. So if I move on, then you'll be able to see some examples here. For each of the following, write the electronic configuration and the Lewis symbols. So this is a chloride ion, this is an iodide ion, this is a sulfide ion, this is arsenic, arsenite, selenium, and then selenium ions. Now, what happens here, depending on what you see, if it forms a negatively charged particle, it means that it has acquired some electrons to form that kind of a configuration. So for chloride here, it is a P5, but then for it to become a chloride, it means that it has acquired an extra electron. So it is going to be a P6. You are moving from a P5 to a P6. The same thing happens here. This is a P4, then you plus 2 electrons, you go to a P6. Same thing applies here. So we can see how these questions have been argued out. So you can see that for chlorine, the atomic number is 17. And therefore, if this is the electronic configuration, now before you add any, before you have added any electron, it was a P5. That's why we have 17. Eh? But when a chloride is formed, then an extra electron is added, and that is why you have P6 there. So when it is a P6, you can come up with the electron dot structure, which is actually the one we have shown down here. Any questions so far? Any questions, students?
Sir, so these dots are showing the total number of electrons that this chlorine ion has.
Yes.
Okay.
And you can see there is a negative because an extra electron has been added. So there are 2 more hands raised. Can we go to Cecilia? Let us start with Cecilia.
Writing Lewis symbol, I have not understood it. Are we considering the 3p6 so that we can put this even 8 dots? I'm not understanding the Lewis symbol, please.
Okay, can we just repeat the question?
I would like clarification on writing Lewis symbol.
Okay, let me go that. Now look, the chlorine has an atomic number of 17. Now, the electronic configuration of chlorine is P5. That's before it forms a chloride. Eh? So when you write Cl, that Cl actually is covering the innermost electrons. So it covers up to S2. So that now what you are showing is this dot here. This is for now for chlorine without the 1 electron that was added. What you write chlorine, and that chlorine actually carries 1s2, 2s2, 2p6, and 3s2. So that now what you are writing, the dots here are showing the outermost electrons, which are 5. Because here a chloride has been formed after an electron has been acquired, then now we write Cl, and then the dots that are going to be there are not 5 this time, but they are 6 because an extra electron has been acquired. And that is why you can see here we have that kind of a configuration, and it is an octet configuration. So if you count all of them, you find that we have 7, then plus the 8th one, you get 8. That's why you can see 2, 2, 2, 2. And then because here it has acquired an extra electron, then it becomes negatively charged. So the moment you write the Cl, if I can write, let me see. When you write Cl, this is written as 1s2, 2s2, 2p6. Then I want to change the color. It has changed everything. That's not what I wanted anyway. So you go to 3s2, then 3p5. So when you write the Cl, you're writing that Cl is standing for this kind of a configuration. And that leaves you with the valency electrons. The valency electrons are the 3s2 and the 3p5. These ones are written as dots. So in this particular case, you're supposed to do 7 dots because we have 2 and a 5. Now, when it forms a chloride, which is actually a negative here, then it forms by adding an extra electron there. They become 6. This means that you now write the Cl to stand for the innermost electrons, but then the outermost electrons are not now 7, but they are 8. That's why we are doing 8 here. Have I answered your question?
Yes, Prof. So that means that this thing is wrong because they are saying the
Yes.
electron configuration of chloride ion is this, and the 3p has 5 only.
Pardon?
Like
Come again.
It is reading that the electron configuration of chloride ion is 1s2, 2s2, 2p6, 3s2, and 3p5, but it has gained an
The
electron.
chloride. Is it the chloride?
Yes.
The chloride
Yes.
has already formed a P6. It is not a
But it has a
P5 now.
P5.
Where?
Your
This one,
slides have
this
a
one here.
P5.
This one.
Yes.
It is me who changed this when I was explaining. Okay? It is me who changed this when I was explaining. This was a P6 for the chloride. It is me who changed to P5 when I was explaining the transition from a P5 to a P6. Is it clarified?
Yeah.
Okay. Let me see other students raising their hands. Yes, Anastasia?
I was asking, now, does it mean it's not possible to write electron configuration for an ion formed with an element that has a d orbital? Like, for example, 1s2, 2s2, 2p6, 3s2, 3p6, and okay.
Let me for the d orbital, when you talk about d orbitals, these are transition metal elements, and actually they form mixed valencies. We are going to mention a few of them, and the mixed valencies are actually cationic. For example, we are going to mention lead 2, we are going to mention ion 2 and ion 3. We are coming to that.
So even in the lowest symbol, the electrons will be still 8.
Pardon?
I'm asking.
Yes.
Will the electrons be 8 in the lowest symbol because they have more than?
Yes, we are going to come up with a configuration such that it is going to be a noble gas configuration, and we are going to illustrate that.
Okay.
Yes, I'll illustrate that when talking about iron. I'll illustrate talking about magnesium and manganese. Grace, can you ask your question?
Excuse me, sir. My
Yes.
internet cut me out when you were explaining why the first ionization energy of magnesium and aluminum drops.
Yes.
I would like you to kind of repeat it for me, please.
Yes. Magnesium as an S2, it is 3S2. The electrons in magnesium are removed from a 3S2 configuration. An S2 configuration is stable. Remember, that is a fully filled configuration, and therefore it becomes difficult to remove electrons from a fully filled configuration. If you look at aluminium, aluminium is 3S2, 3P1. The first ionization energy is required to remove an electron from a P1 configuration, and it is easier to remove that electron because one, it is fully shielded by the inner orbitals. And number two, that is not a stable configuration. Is that
Okay,
understood?
thank you.
Thank you.
Yeah, thank you.
So let me go on, students. So we continue. Now, when we talk about group 3A, and I like calling them group 13 elements, they will show a tendency to form ionic compounds compared to group 1 and 2. Now, the less tendency here is something that we are going to explain. For example, when you look at a group 13 elements, you do have boron, you have aluminium, and you go down germanium, like that. Now, boron, for example, you will find that it does not have any cationic character, and therefore it only forms covalent compounds. So the tendency of group 1 and 2 to form ionic compounds is higher than the tendency of group 13 elements to form ionic compounds. In fact, as you go down the group is when the ionic character increases. So, however, the tendency to form ions becomes greater going down any group in the periodic table. And this one I have said that, for example, as you move to aluminium down, then the ionic character is going to increase. Now, there is a tendency for groups 13 to 15 metals to exhibit two different ionic charges. Now, these two different ionic charges, I am going to explain where they come from. And I'm, for example, going to pick aluminium, and then I pick another compound. For example, I can pick phosphorus. Now, when we look at aluminium, the electronic configuration of aluminium, let me see whether I can write here, text, here. That is aluminium. And then I also want to write the electronic configuration of something like phosphorus. Just a moment. If I write phosphorus, I do a text here. I do phosphorus here. I hope to be able to see them now. We move one up and the other one. So we have phosphorus here and we have aluminium. You know, this one is in group 13. Let me change the way I am highlighting them. You know, this one here is in group 13, and this one is in group 15. Now, what the statement I am explaining is this one here, that there is a tendency for these groups to exhibit two different ionic charges, one that is equal to the group number and one that is less than the group number. So when we are looking that, we may actually call this one group 3 and group 5. Now, so it means that we may have aluminium. For example, here we may have aluminium +3, or we may have aluminium +1. How does that form? The higher charge is due to loss of both the S subshell and the p subshell electrons. So when we have aluminium 3+, it means that that is similar to the group. And that is when we have lost the 3s2 and the 3p1 electrons. We may also have a case whereby we have Al plus. That is when we have only lost what? The 3p1 electron. That's why we are saying that equal to the group number and one which is 2 less than the group number. If you look at +3 and +1, the difference is 2. And this is a result of either losing the s2 electrons or not losing them. But now the chemistry of this kind of aluminum is very rare. Now, on the other hand, if you look at this group of 5, now we may have something like phosphorus 5+, meaning that here it has lost both the S and the P, the S2 and the P3. Or we may have phosphorus 3+, meaning that it has only lost a P. Now, this is an nonmetal, but I want to mention that sometimes you may force nonmetals to behave as cations, to behave as metals, depending on the oxidation conditions that you provide to them. So the higher charge is due to loss of both the S subshell electrons and the P subshell electrons, while the lower charge is due to the loss of the P subshell electrons only. That one I have explained. Now, this slide here is simply showing the periodic table and the numbering of electrons, the groups here is following the long-term numbering of the elements in the periodic table. So you have group 1, group 2, all the way to group 18, where this region here stands for the transition metal elements, and I'll be talking about them actually from the next slide. So look here, when you look at thallium, lead, and bismuth, let me write the electronic configurations of these three, and I hope it's going to fit here. So thallium, just a moment. Thallium, electronic configuration. I hope they are all going to fit somewhere. So if I can write thallium there, a very long one. Maybe I should divide it. What? It may not fit. Are you able to see the whole of it? I have extended it beyond the slide. Then I want to do that of lead. You know, these are elements that follow one another in the periodic table. Now, where do I put this? Let me put it here and also hope that it is going to fit. I may have to bring it down a little bit. And then the other one is bismuth. Did you do the electronic configuration of these compounds? High atomic number compounds? Elements?
Yeah.
Very good.
Yes.
So let me bring this one here and hope it's going to fit. again. So that is what we have. So if you look at this electronic configuration, you realize that this is a P1, this is a P2, this is a P3. So these elements are actually following one another in the periodic table. And if I can go back to that periodic table, I go back to that periodic table, you realize that these are the elements we are talking about. These are the elements we are talking about, 81, 82, and 83. That's what we are talking about. And how do they form cations? They form cations. For example, thallium here is forming cations by just losing the only one electron that it had in the outermost electron energy level, and therefore it is remaining with an S2. Similarly, for lead, it is going to lose 2, then it is going to form an S2. And again, bismuth is going to lose 3. It also forms what? It also forms an S2. So that's important to note. Then the other thing is few compounds of group 4 ions are known. Now, this group 4 is the same as also writing group 14, and I'm going to show you that group. When we talk about ions, we are actually talking about the cationic character of these compounds and the anionic character of the same compounds. And if I bring you here, this is what we are talking about. This is the group we are talking about. This group here, that's what we are talking about. So in this particular group, we do have carbon, silicon, germanium, tin, lead, and flerovium. Now, if you look at what is happening in these particular elements, we know that the chemistry of carbon is predominantly covalent. The chemistry of silicon is also covalent. Now, this one is mixed. This one is ionic, ionic, ionic. Now, why does this happen? It happens because when you look at these compounds, we are saying that few compounds of group 4 ions are known because the energy required to form the ions is very high. The first 3 elements, that is carbon, silicon, and germanium, are nonmetals or metalloids, in the sense that they are metalloid because they are in the middle between metals and nonmetals. But you see, as you go down the group, then you find that their ionic character is going to be enhanced. But the carbon, the silicon, and germanium predominantly are going to form covalent type of bonds. But when you go down to tin, lead, and the fluorovanadium, they actually going to have some ionic character. And that is why we are saying that lead and the tin, which are the 4th and 5th elements of the group, will actually form ionic compounds with 2 ions. Now, these ionic compounds, we are going to explain, it could be 4+ or 2+, but again, I'm going to discuss which of the 2 is more stable than the other. Now, we go on. When we look at the monoatomic ions, we say that cations of group 1 to group 3 have a noble gas or pseudo-noble gas configuration, and the ion charges are equal to the group number, so that group 1 will have 1+, group 2 will have 2+, and group 3 will have 3+. Now, cations of group 13 to group 15 that have NS2 configurations, the ion charge is equal to the group number -2, and I have explained this. This is because it has only lost the electrons in the p subshell, and the electrons in the n subshell has not been lost. And examples are, for example, we have thallium, we have tin, we have lead and bismuth. All these are going to be -2 because they have only lost the electrons in their p suborbital. Now, anions, when you talk about anions from group 15, yes, somebody has, there are 2 students who have raised their hands. Let me start with the Mogeni.
Okay, my question on this one's on lead and bismuth.
Yes.
Like you said, they have lost 2 electrons, but for example, for lead, it makes like 2 positive and a 4 positive.
Yes.
So, and you said it only loses 2 electrons.
Yes.
Does it only lose 2 electrons, or it can also lose like 4 electrons?
It can lose 2 electrons to form 2 plus. It can lose 4 electrons to be 4 plus.
Yeah.
Now, when it is lead 2 plus, then it is the p2 electrons that are lost. When it is 4 plus, then it is the s2 and the p2 electrons that are lost. But the stable configuration of lead is the +2. Let me illustrate that. Let me pick the electronic configuration of lead. Let me post it here so that I can explain that. Now, this is the electronic configuration of lead. And you can see I have actually arranged this one according to the order of the energies of the orbitals, the order that we use in filling the electrons in the orbitals. So look, it is going to lose this P2 so that it can form Pb2 plus. And then it can also lose this S2 together with the P2 to form the lead 4. But now the lead 2 plus is more stable than the lead 4 because once this one is formed, then you get an inner kind of configuration which is stable. The S2 is a stable configuration. So the lead 2 is more stable actually. There's something we call the net ion effect. The net ion effect. So that when you have an S2, it is too difficult to remove or to transfer the electrons from an S2 orbital, especially in these particular elements that are, sorry, that have high atomic numbers. Yes.
When the lead is losing the electrons, let's say when it's losing the 4 electrons,
Yes.
it will stay with an outermost electron configuration of the D10.
That is correct. That is correct.
So I don't get the, I don't understand how the lead 4 won't be stable.
Very good. There's something we call inert effect. The inert effect says that when you have already lost these 2 electrons, remember the first electrons to be lost are these ones. Then if you have to form lead 4, then these are the electrons to be lost. Now, the inert effect says this, that it is very difficult to transfer electrons from an S2 for the elements that have higher, high atomic number elements. Okay, you can at your own free time Google or study little about the inert effect.
Okay, thank you.
Okay. So let me do away with this so that I can continue explaining. So we are saying that the anions of group 15 to group 17, they have noble gas configurations or pseudo noble gas configuration, and this results from them acquiring the suitable number of electrons so that they can have a stable configuration. Now, when we talk about polyatomic ions, these polyatomic ions are held together by covalent bonds as a group, and that this group will either have gained or lost one or more electrons to form the polyatomic ions. And examples of polyatomic ions, you can see carbonates, nitrates, sulfates, and such kind of compounds. Now, when we come to the transition metal elements, somebody was asking me about the loss of electrons in the D block elements. Yeah, the transition metals, you know, the D block, and the lanthanides, and that kind of elements. So how do these elements lose electrons? Now, the electrons are first lost from the ns orbital, followed by the n-1d orbitals. And if I can get an example of, let me bring nickel here. Let me bring nickel. Because nickel is a D block element, then this is where we are. So that is the electronic configuration of nickel. So where are the electrons going to be lost? For nickel to form N2 plus, it is going to lose electrons from the 4s2. So nickel 2 plus will have a configuration minus the 4s2. Now, if it has to form nickel 3 plus, then the third electron is going to be lost from the 3d. That's why we are saying ns, then n minus 1. You know, the ns, this is 4s, then n minus 1 means 3. So 3d. So it is going to first lose electrons from the 4s. And if it is required to lose more electrons, then those electrons are going to be lost from the 3d. Therefore, if we are forming N2 plus, then N2 plus is going to be the electrons lost from the 4s2. That if we have to form N3 plus, then that is going to be D7 here because an extra electron is going to be lost. So that we have a total of 3 electrons lost. So we are saying that many transitional elements also form +3 ions by losing 1d minus 1 electron in addition to the 2 ns electrons. And this is exactly what I am saying or what I am explaining here in the nickel case. Okay. So let us look at what is happening in manganese here. You know, the atomic number of manganese is 25. So the electronic configuration of manganese is what you can see here. Now, for it to form manganese 2 plus, then it is these 2 electrons that are going to be lost. So that the electronic configuration is going to be a D5. Very important to look at here is when it has formed a D5. You know, a D5. Yes, Anastasia, you've raised your hand.
Yeah. May you please go back to the previous slide, please?
That is where we are now.
Is it possible to represent the ion of nickel in Lewis formula?
Yes, you can do that.
How?
Now, when you have, let me go back to the nickel itself. That is nickel. Okay.
Yeah.
Now, when you write the Lewis, the nickel itself is going to have that kind of a configuration. Can you see that?
Yeah.
Then the other 10 electrons are going to be surrounding it. They're going to be another 10 electrons. Now, we'll be talking about configurations where some atoms are electron-less while others are electron more. I am going to be explaining that as we go on, because I know what your concerns are. Okay? Yes.
Okay.
Yes. I'll be explaining that thing towards the end of this, although I can see we are moving very slowly. So look, when we have this, then the manganese here is going to lose 2 electrons to form manganese 2. And you know that we also have manganese 7. Manganese 7 is when all the 3d5 and the 4s2 are lost. But in this particular case, we are forming manganese 2. And when we are forming manganese 2, we have a 3d5. Now, 3d5 is going to be a stable configuration because a d orbital can accommodate a maximum of 10 electrons. I can hear somebody talking. Is it a question? Steve Denver? Okay. So a D5 is going to be okay because it is going to be a half-filled orbital, and a half-filled orbital is stable. Now, when you look at what we have here, you give the electronic configurations of the following: is bismuth and bismuth 3 plus, nickel 3 plus. I think I have explained this. Copper is of interest. Did you find something special about the electronic configuration of copper?
Yes.
Yes. Because of what?
It borrows electrons to form a stable.
It redistributes the 3d and the 4s electrons so that the configuration is stable, isn't it? Very good. I think that you are aware of. Then you can also try to do this and see what you're going to get. But remember, all these, this is a p block element. Bismuth is a p block element. The other two are a d block elements. So here you are losing the first electrons are being lost from the p. Then after the p, you go to the s. Here you are losing from the s. Then from the s, you go to the p. Here you are losing again from the S first, then from the S you go to the P, just like we have done in the previous slides. Now, the following are electronic configurations of some ions. Which one would you expect to see chemical compounds? Now, we have ion 2 plus. This forms a D6. Now, the question is, do you expect some compounds of ion 2 plus? Yes, there are some compounds of 2 plus. For example, ion 2 oxide, we do have some compounds, but predominantly the stable chemistry of ion is that of ion 3, because it is going to form ion 3 by losing another electron, and by losing another electron, this becomes a D5. And you know, a D5 is going to be more stable than a D6 because it is going to be a half-filled. Now, this is a nitrogen 2 plus. Now, nitrogen 2 plus is not going to form any compounds because the configuration here is unstable. But if it is nitrogen, 2 minus, sorry. But if it is nitrogen 3 minus, then compounds are going to be formed because now that becomes a P6. Now, zinc here is D10. D10 is a stable configuration, and therefore compounds are going to be formed. This one, you are not going to have any compounds because this is forming a P5. You are not going to have any compounds with a P5. But then for calcium, this one is going to have compounds. In other words, we are saying that there are no compounds known of this configuration. There are no compounds known of this configuration. There are some compounds known of this configuration, but we have more stable compounds formed. And I think that one is explained here. You know, for ion 3, ion 2 plus, which is a D6, some compounds are going to exist, but stable compounds are those of ion 3, which is a D5. When you look at nitrogen 2 minus, we are not going to have any compound because nitrogen will gain 3 electrons to form some chemistry of 3 minus. Zinc 2 plus is okay because it is a D10. D10 is a stable. Sodium 2 plus is not going to exist because it has only one valence electron and it can only form sodium 1 plus. For calcium, that is what you expect, because no, calcium is supposed to be a D10. Is it a D10 somewhere? No, yeah, calcium is P6, because it was a 3s2. And then that 3s2 actually disappeared. 4s2, sorry, 4s2 disappeared in the formation of calcium 2 plus. Now, what follows here is colors of some of the ions. And the colored ions here are those of the transition metal ions. They form colored, colored ions. Then I want to briefly talk about what we call the ionic radius. I mentioned actually some aspects of ionic radius last time we were discussing, and therefore this is going to be very brief. I'm going to mention and then we move on. So ionic radius is a measure of the size of the spherical region around the nucleus of an ion within which the electrons are most likely to be found. While ionic radius, like atomic radius, can be arbitrary, it can be measured in ionic compounds. And we said that we can compare the atomic radius and the ionic radius, whether it is cationic or anionic, and that is what I am showing here. This is an atom of sodium, and this is a cation of sodium. And you can see in the transition from an atom to an ion, an electron is lost. And when an electron is lost, the effective nuclear charge here increases. And when the effective nuclear charge increases, the size of the particle becomes smaller. We said this last time. When we look at chlorine, this is the atom of chlorine. This is a chloride ion after gaining an extra electron. And here we know that the effective nuclear charge is going to decrease. And then there's also going to be increase in the electron repulsion, so that the ion here is bigger than the atom. I think that one we said. Now, the trend of these particles, we have the ionic radii of the main group elements are shown here. And the pattern here is similar to that of the atomic radius. We said that last time, and we explained why. Now, of importance to talk about is something we call the isoelectronic series. Isoelectronic series are those species whose electronic configurations is the same. So the term isoelectronic refers to different species having the same number of electrons. And a very good example is neon, sodium, and the fluoride. Now, if you go to neon, what is the electronic configuration of neon? What is the electronic configuration of fluorine? What is the electronic configuration of sodium? Now, sodium, you have 1s2, 2s2, 2p6, and then 3s1. That is the sodium. So when it forms sodium plus, it is this, sorry, it is this that goes. So that is what you get. So that is what you have, sodium plus. What about fluorine? Fluorine is a 1s2, 2s2, 2p5. But once it forms a fluoride ion, it acquires an electron, so you get a p6. So that is fluoride, a fluoride ion. And that configuration is also the same for the neon. So you'll realize that these three have the same electronic configuration, and then we say that they are isoelectronic species. The ionic radius for these species is going to decrease with the increasing atomic number. Ionic radius is going to decrease with the increasing atomic number because of the increase in the effective nuclear charge. And that is illustrated, for example, in this. You can see there is a bromide, selenium, and a strontium. If you look at them, then you can see this one follow one another, and this one is down in a different period. Then if you look at them in terms of the increasing ionic number, then you can see that the strontium is going to have this size, the smallest size, followed by bromide, followed by the selenide ion, because of the increasing effective nuclear charge. Now, what we have here is, with an explanation, arrange the following in order of the increasing ionic radius. Again, you look at what is the order of their nuclear charge. You can see. And these are basically isoelectronic series. Then based on the description or explanation that we have already given, and then you can arrange them. Ladies and gentlemen, I'm losing my voice. I want to take a very short break to take the attendance before we continue. So I want to go to the attendance. Okay. Just a moment, I load. So we can begin with Y. Let me load Y. So for Y, we begin. Abdinor?
Yes, present.
Okay. Alice Alamo? Alice
Present.
Alamo.
Present.
Anei?
Present.
Daniel Bilim? Daniel.
Present. Present.
Then we have Samuel.
Present.
Leju? Leju?
Present, sir. Present.
Okay. Lillian Kembabazi?
Present.
Then we have Lucy Lojore.
Present.
Isaac Makuku.
Present.
Evie Moshere.
Present.
Prince Moses.
Present, sir.
Grace Mugambi.
Present.
Angela Murithi.
Present.
Mary Murunga. Mary Murunga.
Present.
Michelle Murunga.
Present.
Prudence Ndiritu.
Present.
Charity Njuguna.
Present.
Barbara Omenya.
Present.
Yesh Patel.
Present.
Cecilia Salempo.
Present.
Umhonza. Axela. Umhoza.
Present.
Lucy Wainaina,
Present.
Naiguran Winnie.
Present.
Any student in this class who has not heard their name?
Yes.
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 Who is the student?
Patience, Marie.
Huh?
Patience, Marie.
Patience.
Group Z, patience.
Are you in this class?
No.
Just pay attention, okay?
Yeah.
Yeah. So we go to the other class. And we begin. Anita.
Present.
Nicholas Amesowe.
Present.
Obwoge Denver.
Present.
Lydia Edosa.
Present.
Isabella Gana.
Present.
Lillian Gishego.
Present.
Al-Amin Hassan. Al-Amin. Can we mark you absent? Asna Hassan.
Present.
Janowala.
Present.
Edith Kisoka. Eldin Kisoka.
Present.
Michelle Mogusu.
Present.
Then we have Joy Mushemi.
Present.
Anastasia Munjuri.
Present.
Philip Mutinda.
Present.
Alice Odiwar.
Present.
Maria Patience. Console. This is one who said that they didn't hear their name.
Present. Present.
Yeah, this is when we are calling you.
Thank you.
Arash Kushrana.
Present.
Sebata.
Present.
Grace Tuku.
Present.
Lois Lorraine Wainaina.
Present.
Njoki Waweru.
Present.
So we are done with the attendance. We go back to our class. I've taken a break. So this is something as students you can do. So we move on to the covalent bond. This is just showing the periodic table. So I want us to move to the covalent bond, and we say that a covalent bond is a chemical bond formed by the sharing of a pair of electrons. Now, in some cases, some elements may have no electrons to share, but they still want to have a noble gas configuration. So in such cases, electrons are donated by neighboring atoms. That's why we are saying that in some cases, one of the atoms provide both of the shared electrons, and such a bond is what we refer to as dative or coordinate kind of a bond. Now, to consider how a covalent bond forms, we actually monitor the energy of two isolated hydrogen atoms and see how they move closer to one another. And this is actually illustrated by a diagram that I'm going to show, but simply the energy decreases first gradually, and then more steeply to a minimum. And as the atoms continue to move closer, the energy increases dramatically or significantly. And the distance between the atoms when the energy is at minimum is what we call the bond length. And all that literature is summarized here. You can see the changes in the energy. And what causes this? Remember, when you bring two atoms together, now, for example, hydrogen, as you can see here, as the hydrogen atoms move closer, the electrons of each atom is attracted to both its own nucleus and the nucleus of the other atom. And the electron probability distribution is illustrated by what you can see here. So you have a hydrogen with a 1s1, another hydrogen with a 1s1. Then when they come together, there is actually overlapping of the 1s orbital. And then we do have a different kind of, the shape of the orbital actually becomes distorted once that particular bond is formed. Now, what are some of the properties of covalent compounds? The covalent compounds, number one, they are known to have very low melting and boiling points. Actually, most of them are actually volatile. And they may be liquids or gases at room temperature. And these molecules are not attracted towards each other by the strong electrostatic forces like we saw. Yes, Samuel, you have raised your hand.
Yes, I didn't understand the bond length. Maybe you can repeat.
The bond length, eh?
Yes.
Let me explain it this way. You have an atom of hydrogen here and another atom of hydrogen here. Now they are coming closer to one another, but now there are competing forces. What are these competing forces? The electron here is being attracted to the proton in the neighboring atom, while at the same time, it is being attracted to its own nucleus. And the same case applies to this. Number two, as they come closer to one another, you are actually trying to bring the two electrons of the two atoms together. So they will come close, but there is an extent to which they can't be closer anymore, because at some point there will be sufficient electron repulsion. That's why I'm saying they are competing forces. The electron in here, let me highlight this. Just the electron here is being attracted to the proton here, and it is being attracted to the proton here. Those are competing forces. And the same electron here is facing the same. Now, as they come closer to one another, there is an electron here and an electron here that are coming closer. Now, the question is, to what extent can they come close? They'll come close, but at some point, even though there is an attraction between this electron and this nucleus here, there's going to be electron repulsion. So at some point, they will not touch one another. That's why actually we say that the orbitals are only going to overlap. And when the orbitals overlap, we look at the closest distance between the nucleus here and the nucleus here, and then that is going to give us the bond length. Are you answered?
Yes, thank you.
So we go on. So there are low solubility in water. We know that covalent bonds, especially if they are non-polar, they don't dissolve in water. So covalent bonds do not contain ions and therefore do not mix readily with water molecules. And they tend to dissolve readily in non-polar organic solvents such as benzene, tetrahydrofuran, and those kind of. But you see, those that form polar covalent bonds, like alcohol, like water, they are going to be soluble in water. Even hydrogen chloride gas is soluble in water because of the polarity of the bonds. Now, they do not conduct electricity. So why? It's because they do not have mobile ions. Now, what follows here is the illustration of formation of a coordinate or dative bond. So a coordinate bond is formed when both electrons of the bond are donated by one atom. And for example, you can see ammonia here. Ammonia is a compound where the nitrogen or the central atom has a lone pair of electrons. Then you bring hydrogen plus. Hydrogen plus has no electrons at all. It has already lost the only electron that it had, but it still has a chance to accommodate 2 electrons. So it comes with nothing, but it is yearning for 2 electrons. It wants 2 electrons. But because there is a lone pair of electrons here, a non-bonding pair of electrons here, then this non-bonding pair is going to be donated so that it can be shared with this hydrogen here. And that is when the ammonium ion is formed. So the 2 electrons forming the bond with the hydrogen ion were donated by the nitrogen. And these are what we call the lone pair of electrons. And the ones shared, they are indistinguishable from the other one. And because of that, then you can see what happens. So we continue. What we call the polar covalent bond. I remember I briefly talked about this last time. A polar covalent bond. A polar covalent bond, I illustrated this when I was using the water, where the bonding pair of electrons are shared not equally. They are close to a more electronegative atom than to the less electronegative atom. And I was able to show that the one that almost loses the electron forms partially positive partially positive charges. And the one that almost loses the electrons forms partially negative. The one that almost gains electrons forms partially negative charges. And that ends up giving us a polar covalent bond, or what we call a polar bond. So, and this comes from the electronegativity. I think I have explained that before. And there's a student who asked me how to assess whether the level of polarity, non-polar, polar bond, or the extent of the ionic, depending on the difference in the electronegativities. Anita, you have raised your hand. Please ask your question.
Yeah, I just wanted to ask, so can we say that all polar bond, all polar bond compounds form, they form those large angles between their bonding elements?
Come again? Which large angles?
Let's say water, the water stuff.
Yes.
Let's say oxygen and hydrogen.
Yes.
So if it is a polar bond,
Mm.
so do we expect a large bonding angle?
Now, the bonding angle actually is dependent on other factors, which we are going to be looking at when you look at the geometry. Can we reserve it for that?
Okay.
Yes, we'll be looking at the geometry and the shapes of compounds, and that one should be coming on Wednesday. I think we can look at it at that, because when we have non-bonding electrons or lone pairs of electrons, they are going to have their own forces, and those forces are going to impact on the bonding electrons. There's going to be some extent of repulsion, which is going to actually result into some bond angles, like you see in ammonia. So can we discuss it at that?
All right.
Unless there is a burning clarification that you wanted us to look at. Yeah. Or do you want to ask why we write water like this?
Yeah, like I just want to know
Yeah.
like how you can know that this is a polar bond and this is a plain non-polar.
Okay, I get your question. You know whether it is a polar bond depending on the difference in the electronegativity of the two compounds involved. I talked about it shortly, and I'm also going to show some values, I think, in the next few slides. Okay, the difference in the electronegativity of the two atoms or the atoms in question is going to tell you whether the bond which is going to be formed is going to be non-polar or polar or even ionic. There are some values I showed in the first lecture, and we may revisit them. I don't know, maybe in the next few slides we may look at them.
Okay.
Okay. So we move on. This is electronegativity. We said it increases as somebody moves from the left to right. And you know why? It's because of the increase in the effective nuclear charge. That's why we are saying that the halogens have the highest electronegativity, while the group 1 elements have the lowest. In fact, they would choose to lose electrons rather than accepting electrons. What you are asking is actually here, the difference in the electronegativity between the two atoms in a bond is a rough measure of the bond polarity. When the difference is small, then the bond formed is non-polar. Sometimes the difference is even zero, like when you have hydrogen and hydrogen, these are two elements of the same electronegativity. And therefore, if you get the difference in the electronegativity, it is going to be zero. When you have nitrogen and nitrogen forming N2, then that is non-polar because the difference in the electronegativity is going to be zero. So large differences are going to result into polar bonds, and very large differences are going to result to ionic bonds. I was able to show some values that determine this, but we can see some values in the next slide that I'm going to show. So using electronegativities, arrange the following bonds in order of increasing polarity. pH, the difference is 0. Oxygen and hydrogen, the difference is 1.4. Carbon and chlorine, the difference is 1.5. So if you look at this, for example, this one here is going to have the lowest polarity because the difference is 0 here. It is going to be followed by this. And then the highest polarity is going to be found here. When we will have, maybe I will introduce those values somewhere in one of the slides, and then we revise, we upload an updated notes for you students to see, because those values are not actually captured in this slide, but I was able to show you last time. Now, during bond formation, the electrons are piled towards the more electronegative atom, and that is what I said when you say that they are closer to the more electronegative atom. The direction of the electrons can be predicted using the electronegative scale. For example, when you look at the hydrogen chloride bond, the electrons are pulled more towards the chlorine because it has a higher negativity than they are towards the hydrogen, because the electronegativity here is 2.1. When you get the difference between the two, you are going to get a particular number. But what I can say is that what is formed here is a polar covalent bond. So the chlorine atom acquires a partial negative charge because by virtue of having the electrons closer to it, it is almost acquiring the electrons, but it has not fully acquired. And because of that, it is going to have a partial negative charge. While the hydrogen acquires a partial positive charge because it is almost losing the electrons, but it has not completely lost. And therefore, it is going to have a charge of that kind of a nature. So this is going to be a polar covalent bond. And if you look at this, then this is an exercise here that students you can look at. There is also another exercise here that you can look at. Arrange the following bonds in order of increasing polarity. Well, you are already given the electronegativities of the elements, then that one you can look at. We have 4 minutes. So in that 4 minutes, maybe I'll look at this. So Lewis electron dot formula. In the past, we were looking at the electron dot formula of elements, whether they are losing electrons or whether they are gaining electrons. In this particular case, we want to see what happens when compounds are formed, when covalent bonds are formed. So a formula using dots to represent valence electrons is called the Lewis electron dot formula. And this electron pair is represented by 2 dots. An electron pair that is between 2 atoms is a bonding pair. And it can also be represented by a line for each bonding pair. Now, electron pairs that are not bonded are non-bonding, or we can also call them the lone pair of electrons. And here, in forming covalent bonds, the atoms tend towards having a full 8 electrons in their valency. And this is what we call the octet rule. But not all of them are going to have an octet rule, because for hydrogen, it requires a maximum of 2. And we just say that it is an exception because it doesn't require 8, it only requires 2. So we call it a duet. A single bond is a covalent bond in which one pair of electrons is shared by 2 atoms. Now, that shared pair of electrons may be donated by 1 atom, in which case we call it a coordinate or dative bond, or the 2 atoms may be sharing the electrons equally. As in, you donate 1, the other one donates 1, and then they are shared in the bonding. A double bond is a covalent bond in which 2 pairs of electrons are shared by 2 atoms, while a triple bond is a covalent bond in which 3 pairs of electrons are shared by 2 atoms. Double bonds form primarily between these types of atoms. Now, I want to stop there for today's students. Then say that we'll be having another lecture at 3:30 today, so that we can try and complete the work for today. There are, however, 2 students who have raised their hands. Let me begin with Anita.
No, sorry, that was the previous hand. Sorry.
Okay, Mogeni.
I wanted to ask if it's possible for you to upload the recordings of the past class and this one.
Yes, I will do that. I'm told that we have to convert, we have to do some view conversions. So I'm going to consult my colleague and we're going to do that. It was actually raised at the beginning of the lesson. Yes, Yasin. Mugen, you're not through. Just wait. Mugen, you're not through.
Yeah, I'm done.
Okay, yes, Yasin.
It's not a question, but Prof, I wanted to inform you that I'm present. You marked absent. I believe so.
You absent, eh? What was that?
No, I had a blackout in my area.
Okay, I will review that. Then Hamed, Asna.
Excuse me, sir. I wanted to ask in the exercise, there were 2 exercises. The one before, I wanted to ask if you could clarify how we should do it.
Now, I will ask Dr. Naomi to clarify about those exercises. I think some communication will be coming to all of you. I hope all of you are in the group chat.
Yes.
Yes, I will ask for clarification and it will be done.
Okay, thank you.
So thank you, students. We meet at 3:30 today. Bye.
Bye.
For
Bye.
now. For now.
Bye.
Bye.
Thank you.